Welcome to video number 2. Today we're going to launch right into Sky's paper that attempts to prove the Landau hypothesis and thereby prove the Riemann hypothesis. Sky's paper begins and introduces a function called W of n. This is a new function that's invented by Sky, and it's the main focus of the proof. But we won't be addressing W directly, not in this video. First, we need to talk about psi, which is used to define W. And we're going to need some time to, just wrap our heads around this expression, psi. So let's get into that. For each n, positive integer n, we're going to take each of the terms, p to the k, from its prime factorization and put them into the function psi. Psi takes the whole value, p to the k, as the input. If it helps you, you can think of that as a function of two variables, like separately on p and k. It works either way. We do need to be clear, though, that for any given n, we're not going to be calling psi twice for the same prime number. So k needs to be the full exponent, representing all the powers of p that divide n. In other words, k is specifically that exponent that we were displaying in video 1 when we talked about the fundamental theorem of arithmetic. Anyway, in part, it's going to return this expression, and let's focus just on p minus 1 over p first. So p is some prime number. So this takes values like 1/2 or 2/3, 4/5, 6/7, and so on. But for big prime numbers, this gets quite close to 1, right? Always just a little bit less than 1. Okay, so we have some value between 0 and 1. We then raise that to k and then subtract that from 1. So k might be 0, it might be 1, it might be 2, or some higher number. If it's 0, anything raised to the 0 power just turns into 1, and 1 minus 1 is 0. So when k is 0, this expression is 0. If k is 1, then we just have p minus 1 over p. And 1 minus that is 1 over p. If that's not perfectly clear, you can just think about a numeric example and you'll see it instantly. If p is 43, then we have 1 minus 42 over 43. And clearly that's going to be 1/43. Let's just do an example where we look at a lot of different values of k. We'll set p equal to 5 for a minute. So p minus 1 over p is 4/5, or 0.8. And the powers, as k grows, look like this. So it goes from 0.8 to 0.64, and then to 0.5 something, and then to 0.4 and change, and 0.3 and change, and so on. And as k goes up, the p minus 1 over p to the k keeps dropping. But no matter how high k goes, it's never quite going to reach 0, right? It compresses, and there's always just some tiny amount left. By the time k is 20, you've got it around 1%, and it's dropping a little bit at a time. And we're going to have 1 minus that. So actually, the whole expression is rising, and it starts rising slower and slower. As k gets really big, now we're approaching 1, but we're never quite getting all the way to 1. As we say in the math world, it gets arbitrarily close to 1. I'm going to say arbitrarily a lot in this video series, okay? It's a term of art. It means, in this case, it means if we are free to pick whatever value of k we want, we can get that expression as close to 1 as we want it to be. If you're into graphs, it looks something like this, right? So orange is before we subtract from 1. We see it declining slower and slower. And then blue is after we subtract from 1. So we've just flipped it on its head, and it's approaching 1. All right, let's sum up what we just covered. For k equals 0, this expression is equal to 0. And then every time you increment k, this rises. It gets bigger. And eventually it'll get close to the value of 1, but it never quite will reach 1. All right, so we're straight on that. Now let's add one more piece to the expression. We're going to multiply by 1 over p squared. And as before, we want to think about this as holding p constant while we let k vary. That's the way to think about it. So the earlier version was varying from 0 to almost 1. This version is varying from 0 to almost 1 over p squared, which is pretty small itself. So the whole thing has the same shape, but it's been scaled way down to have a much smaller maximum value. Now imagine for a second that we're summing up a bunch of these for different values of p, because that's what we're going to do. In fact, let's return to our idea of the exponents of the primes being like the identity of a positive integer n, right? For every n, we're going to define a function of n that sums this expression over every prime number. Let's call it u of n. Now, okay, u of n isn't exactly the result that we're going to be looking at in future videos, but it's close enough to think our way through the part that we're focusing on at this moment, okay? We'll order the primes and index them by j and sum the function psi over all j's, right? Each prime will be raised to a power k that corresponds to the prime factorization of n. So n determines the value of k sub j. But recall that most of our exponents k are 0, right? And when k is 0, the expression on top is 0. So practically speaking, we only need to sum this up over the primes that actually make up the prime factors of n. Maybe we'll do an example before we move on. Let's take the number 12. Okay, so 12 is 2 squared times 3 to the 1. So we're going to call this expression twice, basically. We're going to, in the first time we call it, p is 2 and k is 2. That gives us 1/4 times 1 minus 1/4, or 4/3. So 1/4 times 4/3 is 3/16. And then the second time we call it, we're going to have p equals 3 and k equals 1. And that turns into 1/9 times 1 minus 2/3, or 1/9 times 1/3, which is 1/27. And then finally, we just add those two numbers together, and we get something around 0.2245, thereabouts. Okay? Makes sense. All right, so now we consider this as a function of n, and n could be any positive integer. So, question for you. What is the range of possible values that we should expect for u of n? Well, we could start by looking at n equals 1, which is a unique case, right? 1 has no prime factors. All the k's are 0, so all the psi functions return 0, and the overall sum is 0. Now from there, the rest of the integers have prime factors. We'll be incrementing some of the k's. And we just learned that if you increment k, you always increment the output by some amount, so it rises. Now, we haven't quite finished building this function psi, but let's just pretend that we have for a second. Each time we call this version of psi, it returns a value between 0 and 1 over p squared, right? So imagine that you're trying to max this out by finding the value of n that gives you the biggest output. So incrementing k for any given prime number always gives you a bigger value. So to max this out, you just want lots and lots and lots of prime factors. You just multiply over and over again by all your favorite prime numbers until you get some, ridiculously large value of n. And u of n is still returning a value that's limited by the sum of 1 over p squared over all the prime numbers, right? If each prime's contribution has an upper limit of 1 over p squared, then of course the upper limit of the whole is the sum of all those limits. And we're just going to call that a constant, capital G, okay? So it turns out G is something like 0.452 or something like that. It doesn't matter what the value is, right? It just matters that it exists and it serves as the specific upper limit to the values that come out of the expression that we're building. So the next thing we want to do is use g as a constant to helpfully rescale this whole thing again, which of course rescales the overall sum u of n by the same quantity. And in the final version of psi that we're building, we actually want the upper limit of u of n to be equal to the number pi for reasons. So we're going to use this expression to do that. So now we have completed the definition of psi that's found in the paper. All right, psi equals pi divided by p squared, also divided by g, times the rest of that nonsense. We divided by g, which rescaled the whole thing to between 0 and 1, basically. And having done that, then we multiplied by pi. So now these sums range from 0 to a limit of pi, which is what we want. Just make sure you're clear, though, that pi isn't the maximum value of calling psi once. It's the limiting maximum of calling it over every prime number and choosing super big values of k every time to try to inflate that end result that we're calling u of n as much as possible. You might say that we've divided up the space between 0 and pi into some chunks. And each chunk belongs to a prime number. And each of those chunks bears a relationship to the whole that's equal to 1 over p squared divided by g. These are the potential spaces dedicated to each prime number if the value of k for that prime was like super big. And then, within each chunk, we have smaller amounts that actually get used according to what the value of k is. The smallest subchunk is for the first power of p that we find. And then you would use a bit more if there were 2 powers of p, and so on, more and more, closer and closer to the full available chunk. And for a given n, an integer n, we're going to call psi a bunch of times, and we add up whatever parts of this are actually used to get some value that we know is between 0 and pi. So now we know what psi looks like and how it behaves. And we know that we're going to be adding up its outputs for each value of n. The final section of this video is to discuss the uniqueness of this summed output. If I chose 2 possible integers of n, and for each one I plugged all of its prime factors into psi and added up the results, could I ever get the same output, same sum for both n's? Well, no, as it turns out. No 2 integers are going to give you precisely the same output. And I'm going to give you a little argument for why that is. We will ask the question, given one output of this type for an integer, if we don't know which positive integer n came from, could we figure that out? And the answer is yes. So imagine that we're given some value u, and we know it came from a sum, like the one on the screen. How do we do this? Well, the first thing we can do is we can take that number u and we can divide by g, and we can divide by pi, right? That'll remove the common elements that we know are present. And then we know we have some sum of expressions that looks like this. Now, clearly, each of the individual psi's is now, well, a piece of psi, right? We've divided out some pieces. What we're left with is a rational number, right? A fraction of whole numbers. We can see that just by looking at it. And of course, the sum of a bunch of rational numbers will itself be a rational number. So at this point, we have a fraction, right? We could potentially simplify the value by removing any common factors from the numerator and denominator, just like they taught us in grade school, right? But given that single rational number that we know is the sum of more than one of these terms, maybe a lot of them, is it possible that we can always like untangle them from each other? And if we can, then the outcomes must be unique, right? Because it would mean that all the information about which P's and which K's were used to build that output are still encoded in the number itself. So let's apply some algebra. We're going to do a little bit of rearranging here. We'll convert this part to two separate expressions, each raised to the k power. We're allowed to do that. And we can replace that 1 with pk over pk. And now we combine inside the parentheses, and we get a fraction, right? We'll move that to the top to get a little more space to work with. We have p minus 1 to the k up here, and we know how to multiply that out for any k, right? There's going to be terms for each power of p, and there's going to be constants attached to those, and they depend on k. But, you know, the first and the last terms are knowable. And actually, the second one is going to be minus kp to the k minus 1, right? That'll happen every time. This might be a long list of terms, but we know that it follows a regular pattern, right? And we know that every power of p between 0 and k is present in there in some form, you know, with some constant. Finally, the p to the k's cancel, right, on the top there. And we can combine the denominator too. We can get p to the 2 plus k. And so now we have a fraction, right? Now we have a rational number very clearly. And don't forget, we're looking at actually a sum. But each of the things being summed can be thought of in this form, right? Now, there's one thing that we can very clearly observe about this polynomial in the numerator here. And that is that it is not divisible by p, because it only has one term in it that doesn't include p, and that's the plus or minus 1 at the end. So you have a number divisible by p plus or minus 1. So clearly that can't be divisible by p. And the fact that it's not divisible by p means that this fraction, the way it's like currently expressed, is already simplified. It has 2 plus k powers of p on the bottom and no powers of p on the top. If we put some actual numbers in for p and k, and we just do the arithmetic, before we do that, we already know that we will get a rational number that is already expressed in its most simplified form. So far, so good. Now, let's think about what a sum of things like this look like. What do we do when we add fractions? Well, in grade school, they taught me to cross multiply, right? Let's generalize, and we'll show 3 fractions being added. And then of course, there might be many more, but I think 3 is enough to illustrate the pattern. Okay, a over b plus c over d plus e over f equals all this stuff, all over b, d, f, right? The product of all the denominators. And each term in the numerator takes a or c or e and multiplies it by all the denominators except for its own, right? So a is not multiplied by b up top, but it is multiplied by d and f. So here's the question. Is anything in that denominator, b, d, f, going to cancel out when we simplify this fraction? That sum on the top looks like it could be almost anything, right? How do we know that if we put some numbers into this, we don't somehow lose the information that we want to keep, which is in the denominator, right? The denominator can tell us which p's and which k's went into building this sum. Well, as it turns out, no, nothing is going to cancel out. Why not? Well, let's consider b first, right? So b is some prime number with a power greater than 2, and d and f are other prime numbers also raised to some power. And none of the other denominators, d or f, have any of that particular prime number that makes up b, right? So if we see that there's some powers of 5 contained in the denominator of our sum, we know that they all came from the same place, right? Now, let's look at the numerator. I'm going to claim ADF is not divisible by B at all. How do I know that? Can you see it? Well, A over B was already a simplified fraction, right? We know that part. So clearly, A isn't divisible by B. And D and F are made up of other prime numbers, not the prime numbers that make up B. We just talked about that. And the rest of the numerator is divisible by B due to the cross product approach that we use to build the fraction, but not this one term, ADF. So therefore, just like a moment ago when we had plus or minus 1 at the end of a polynomial on B, B cannot divide the numerator here evenly because it divides all of it except for that one last piece. And the same argument that we made about B is just as valid for D and for F. And therefore, this whole fraction is also, we know, simplified already. There's nothing that will cancel and nothing will be lost. Which means if we are given a sum of size, we can find this denominator, which, when the rational number is expressed in its simplified form, contains exactly p to the 2 plus k for each p to the k that was input. So if our outcome has a denominator and the prime factorization of that contains 7 to the 5th, we can safely conclude that psi of 7 to the 3rd power was one of the original inputs, right? Because if k is 3, then p to the 2 plus k is 7 to the 5th power. And that's what we found. So this argument allows us to conclude that no two integers will result in the same output when you sum the psi function of their prime factors p to the k. Each n will have a unique result. That's all for today. In video 3, we are going to circle back to this part of the paper again, and we're going to talk about W of n and F of s, and we're going to talk about what Sky means when he says that F is a kind of Euler product. Stay tuned.